This is the Unit 4 review for sections 3.1 through 3.5. In 3.1, we had some interest work. We're going to use this formula for monthly interest. We're going to use that the amount is the principal times 1 plus the rate divided by the number of times you're compounding, in this case monthly, multiplied by that same number times the number of years. So we'll plug in 1,000 for the principal, plug in 0.11 for our rate, we'll plug in 12 for the compounded monthly part, and 45 for the years. So if you wait 45 years, $1,000 turns into $138,000 at an 11% interest rate. If we take the same thing but we look continuously, so we use this formula, PERT, and we use E and our rate and 45, it's a little bit higher because we are compounding continuously instead of monthly. For the next one, we're describing transformations of functions. You can see that the 2 all the way in the front here is a vertical stretch. The 4 inside the exponent, right next to the x, is a horizontal shrink. And the negative there is a reflection across the y-axis. This plus 6 at the end means you're going up 6. Next up, the negative at the beginning is a reflection across the x-axis. The plus 6 here is not really left 6 because there's a 2 there. It's actually left 12. You do 2 times 6. And then that 2 times the x gives you your horizontal shrink. And down here we have down 7. Using the 1-to-1 property, we can rewrite 1 over 64 with 4 as a base. So that's going to be 4 to the power of negative 3. Then we can set those exponents equal to each other because they have the same base. So we can say x minus 2 is equal to negative 3. And if you solve for x, you get negative 1. We'll do the same thing here. We'll change 216 to have a base of 6. And we'll rewrite the left side to also have a base of 6. All we have to do is change that exponent to a negative. When we do that, we can set the exponents equal to each other. So negative x plus 3 is equal to 3, so x is equal to 0. For this next one, e raised to these different exponents, we can set them equal to each other. And this sets up a great quadratic. If we add x squared to both sides, we have a quadratic equals 0. If we use the x method to factor, we get this. And make sure that you put your answers as 5 or negative 2 and not negative 5 and positive 2. Very similar problem here. We'll set negative 2x plus 8 equal to negative 7. This one's just linear. The answer is 7.5. How many grams at the start? That's just our initial quantity, which is always in that first position, so the answer is just 25. How many grams after 20,000 years? Well, we plug in 20,000 for t, and this is calculator work. The answer is 2.21 grams. For the question, how many years until there's only 4 grams, you have 2 methods. The first method is to use the calculator. We can plug this in to y equals, and you'll have to adjust your window to a maximum that's a much larger number, like say 20,000, and you could trace until you see your y value at 4, and that would give you about 15,000. However, we can also solve this by using logarithms. Consider that what we're saying is 4 is equal to the principal 1/2 to the power of x divided by 5717, or 5715. So for this last one, how many years till there's only 4 grams? There is the calculator method. You can take the entire equation and plug it into y equals. You'll have to adjust your window to see the graph. One quick way to do that is to change your x max to like 20,000. And then you can trace and follow the graph until you see that y is equal to 4. It's kind of sloppy, but that method works, and it will get you an answer of about 15,000. If you want to jump straight to the answer, you can divide both of these sides by 25. And then you have 4 over 25 is equal to 1/2 to this power. So think about what that means. 1/2 to some power is 4 over 25. So if we take the log of base 1/2, 4 over 25, we get this. And that's what x divided by 5,715 is. So if we multiply both sides by the denominator, we get our answer, which is 15,109. More precise, but good to know this method. The next section, 3.2. 9 to the power of x is equal to 1 over 81. If we write that in log form, we say log base 9 of 1 over 81 is equal to x. We're not solving any of these, we're just rewriting. Log base 7 of 1 over 343 is negative 3. Log base e of 12 is equal to 5x plus 6. And if we wanted to, we could say the natural log of 12. That is just log with a base of e after all, and they're both equal to 5x plus 6. Expanding these into exponential form, we can say 8 to the power of 2/3 is 4, e to the power of 6x is 4, because remember the natural log is just log with a base of e. And 6 to the power of 4 is equal to 1,296. The one-to-one property says if you have the log base 11 of two things and they're equal, you can set those equal to each other. So 2x minus 12 is x plus 5. Solve for x, you get 17. The same thing is true with the natural log. We can set the x squared plus 21 equal to the 10x. This becomes a quadratic. We set it equal to 0. We use the x game to figure out. Our answers are 7 or 3. If you want to solve this next section on the calculator, you can press Math Alpha Math, and that's pretty easy. Works really well. You can also think about 121 to what power gives you 11? Well, that's going to be the square root of 121, so that power is going to be 1/2. 3 to what power is 1 over 81? Well, 3 times 3 is 9, times 3 is 27, times 3 is 81. And it's flipped, so we make it -4. 3 to what power is 27? 3 times 3 times 3 is 27. The answer is 3. So the negative in the front is a reflection across the x-axis. The 2 in the front here is a vertical stretch. And the plus 6 way at the right is up 6, or translation up 6. In the next one, the 6 here in the beginning means going up 6. You could rearrange it because it's just addition after all. We normally see it at the end, so that's a little confusing perhaps. The negative that's in front of the log is a reflection across the x-axis, and the plus 6 that's inside the parentheses with x is actually left 6. To use the change of base formula here in 3.3, we can think about log base 10 of 220 divided by log base 10 of 15. Or if we're actually just pressing buttons on the calculator, that's log 220 divided by log 15, and the answer is 1.99. We do the same thing for this one, log 81 over log of 1/3, the answer is -4. Now there's multiple ways you could simplify these, so I'm hoping that I'm doing it the same way you're doing it, but we can think about log of 2 over 400 and change that to 1 over 200. Why not? We can simplify it. And I'm going to split it like this because it's, if I split it as using addition, that's the same thing as if you were to multiply those two values. And why am I doing that? Because I know that the log of 1 over 100 will come out as a whole number. Remember that 10 raised to some power equals 1 over 100, that's just going to be -2. So I'm remembering the negative property of exponents here. For this next one, I'm going to split the fraction into subtraction. And then what's really nice about that is ln e cancels out, and we just have 3 minus ln 7. For this next one, if I rewrite the 4th root of 7 as to the 1/4 power, this all cancels out, and we just have an answer of 1/4. If I change 27 to a base of 3 to the 3rd power, these cancel out, we just have an answer of 3. If I put the -7 up in the exponent by multiplying, then ln e cancels out, and I have an answer of -14x. For this one, I'm going to put the -3 into the exponent and the -10 into the exponent. Or actually here I just put the +10 there. And these can both be resolved because ln e goes away, and you have -18 minus 40, which brings you further negative to -58. Since this one has the product of 12x to the 3rd and z squared, you can split them apart into a series of addition. Since this one has the quotient of 4x to the 5th and y squared, you can split them apart using subtraction. This one combines the two. We have some addition and some subtraction. So let's do the exponents first. I'm going to take these, the 4 up there and the 2 up there. And that shows up like this and like this. And then the addition ones go on top, x to the 4th and y squared as multiplication. And I'm going to divide by the subtraction ones. So I'm going to divide by z squared. So with this one, I'm going to move the exponents up to the top. And instead of actually condensing this further, I'm going to leave them as the product of the zeros. So on the top, we have expressions x plus 4 times itself 3 times, x squared, and on the bottom, where you see the subtraction, we have x minus 2. You could actually multiply this out and get a different, more simplified version for the numerator, but I like it like this. If 6 to some power is 216, we can change 216 to a base of 6, and then x has to equal 3. We can do the same thing with 1 over 125. We change it to a base 5. Our exponent there is going to be -3. And we set x minus 2 equal to negative 3, and we solve for x, negative 1. If we add the natural log of 7 to the right, then we can set 2x equal to 7, so x is 3.5. First thing I do here is subtract 3 from both sides. 3 to what power is 27? That's just 3. Next up, I can set x squared plus 21 equal to 10x. This is a quadratic. If I subtract 10x from both sides and I use the x game, this is what I get. So my answers are 7 or negative 3. If I take the natural log of both sides on the left side, this cancels out nicely, and I have negative 4x is equal to the natural log of 16. So I divide both sides by negative 4. This is what I would put in my calculator, and the answer is negative 0.69. Here I'll divide both sides by a negative 2 first, and then I'm going to take e to the power of ln 4x and e to the power of negative 13. That allows me to cancel this out on the left, and I have 4x is equal to e to the negative 13. If I divide both sides by 4, this is what I would put in the calculator. That's how it will spit it out in scientific notation. For this one, I'm going to take e to the power of on both sides, and that allows me to cancel out. And then I have the square root of 4x plus 2 is equal to e squared. So if I square both sides, this now becomes e to the 4th. And then I can subtract 2 and divide by 4. This is what I would put into the calculator. It's about 13.15. So I think about the base here of 10. This is saying 10 to the power of negative 2 is equal to 1 minus 3x. Well, I know what 10 to the negative 2 is. That's 1 over 100. So I can replace that and say that if 1 over 100 is equal to 1 minus 3x, well, let's subtract 1 and then divide by negative 3. And that's how I solve for x. The answer is 0.33. Let's complete the table for an investment that earns compound interest continuously. So for the time to double, I'm going to start off with PERT, and I'm going to plug in 15,000 as my principal. E is built into the formula. My rate is 8.5, so that goes in here as 0.085. And I know that I'm going to be doubling, so I can set this equal to 30,000. If I divide both sides by 15,000, I get this. Now if I take the natural log of both sides, the e cancels out nicely. And if I divide by 0.085, I have my answer, 8.15. If I want to find the amount after 10 years, I use the same formula with the same principle, but this time I can actually plug in a 10, and that's just calculator work. In the next row, they give me the initial investment, and they give me the time to double. So if I use that same idea, that the time to double, kind of like I did here, where I eventually got to this point, e to some power is equal to 2, let's jump there, and it's this. We had e to the 12x is equal to 2. And that tells me, once I take the natural log of both sides, this cancels out. If 12x is equal to the natural log of 2, I can divide both sides by 12, and that's how I get my rate. It's about 5.78%. In terms of the amount after 10 years, if you round, you get the bottom number. If you stored it in your calculator and had the precise value, you get the top answer. I'd probably take either one. For the next row, they give me the annual rate and the amount after 10 years. If I want to calculate the initial amount, I can do this. I can divide both sides by e to the 0.065 times 10. So it's 22,000 divided by e to the 0.065 times 10, and that jumps me straight to my principal, which is 11,485. If I want to find the time to double, I can consider that my rate is 6.5, and my time to double here is represented by the 2. So I take the natural log of both sides. This cancels out. I take the natural log of 2 divided by 0.065, and the answer is 10.66 years. For half-life, it's a similar formula, but a little bit different. So the idea here is that we have some principal amount times 1/2 to the power of some amount of time divided by the half-life. And they tell me here that my initial quantity is unknown, but the amount after 1,000 years is 4. So what I did is I plugged in the 4 on the left, and I plugged in the 1,000 years here, and I'm trying to solve for p, or my principal amount. And to do that, I can just divide both sides by 1/2 to the power of 1,000 divided by 5,715. So this part right here plugs straight into my calculator, and I get an answer, 4.52 grams. The next row, they give me a half-life, and they give me an initial quantity. So I can use this to figure out the amount after 1,000 years. 9 times 1/2 to the power of 1,000 divided by 1599. 5.83. For this last one, I like to use exponential regression. So what I did is I pressed Stat Edit on the calculator, and I put in 4 and 6 in the X column, and 100 and 800 in the Y column. And then I did calculate an exponential regression, and I told it to put the formula in Y1. To do that, you have to press the vars key and pull up functions Y1. But if you do that, then you can just go straight to the table, and when X is 9, what is Y? And the answer is 18,102.